in Europe. And just to mention a few, I don't want to extend, but this is really needed because there are a lot of people that probably are not aware of them. Of all these strong efforts that have been put in place, that have been carried out from JSC, but also from the European Commission in general, to, let's say, try to harmonize testing in different laboratories. So what my suggestion for Thomas is to try participating in these, very important electrochemical conferences and try to disseminate, with activities, the results of these activities that will be very, very beneficial for all the education.
And maybe we can also try to make those reports more prominent in our website somewhere, so that people could easily find them. Or if you Google electrolyzer testing protocols, that these would sort of come up.
Find them.
You do find them?
Yes.
Okay, that's good to know.
Maybe a short comment on that. I think ARC has been there a long time. We've got an excellent reputation, and especially this dynamic operation is quite chaotic. We've shown that what could be expected in a network like Belgium. Last week or 2 weeks ago in Jeju Island, the IEA also discussed we don't have an AST, but we can define a drive zone. For me, it's important to know what is the dynamics we can expect, because for them, the dynamics is one of the selling points. There will be batteries, there will be alkaline. ASC may have an overview of what locations could have some dampening effect, some storage, and translate that also to the area of accelerated testing. What cycling should we be doing to mimic reality that is in the area of too much stress, degradation testing, without exceeding this operating window? Knowing where this sweet spot is in between is important. I'd recommend that you make your test protocol available not only in paper writing, but actually have it as a standard protocol in one of these major test equipment operators at the JRC 101.
Yeah, good suggestion. It is difficult to get data, really electricity data, to have. I mean, what you find is really 15 minutes time frame, and even then it is difficult to find quality data and have them numerically available. So the report will also promote where you get the numerical data from. So it will basically in terms of percentage, like this what it is now, and there's quite a huge data set. So if you open them in Excel, you will take some, not only seconds, but it depends on your computer power, minutes to load these data for 1 year, for example. So the numerical data will be made available, so everything there. But it's really difficult to get electrical data anywhere. That is extremely difficult.
There's one more question, but maybe take this one and then we move on. No, it's here.
I have one addition to that. I think it's, as you mentioned, it's very difficult to get these data. And in addition, we don't just need one data set, but we have different use cases where we have the grid connected or just connected directly to renewables, and different renewables in different locations will have different profiles again. And we might need different time resolutions for these different cases as well. 15 minutes might be good for grid connected, but maybe not for direct coupling. So we're actually looking at a whole array of different test profiles, which we would need and which we need to analyze to maybe reduce them to a representative set, which is not too huge test. And we've been trying to find higher resolution in time series profiles, and basically ended up trying to model these from wind data, which is more readily available than grid data. That it's a challenge, but it's worth it. I think.
Yeah, I've contacted different turbine manufacturers as well, and PV, and they say they have some data, but they cannot. They're confidential. They cannot get them out. So it's really difficult to get useful data.
We hope one day we can support a project for a hydrogen-producing wind turbine, and there everything is going to be very clear. Right, Thomas, maybe.
So we move on. This is the next presentation. Yeah, your presentation.
Number 8.
Great. Good morning, everyone. My name is Pierre Millet. I'm professor of physical chemistry at PARIS-SACLAY University, and I'm working as a scientific director at Hydrógeno. So this is why this is a presentation by Hydrógeno. We have joint lab together, I mean, the university and the company, and this is where we have this type of strong link. So the outline of my talk this morning, I mean, I think time is limited, and therefore, I'm professor at university professor, so I'm used to speak. Usually my time slot is 3 hours, so I have to compress it a bit along the time axis as well. So some general features on water electrolysis, and then I will try to review some main aging processes and present some data related to some specific AST that we used for characterization of sacs. General features. So this is very basic slide showing cross-section of what a PEM cell is. You can see it on the left. So it's a multi-layer system. I don't want to enter too much into the details. There are different options. We can use CCM or CCS, PTEs or GDEs or GDL or whatever. There are different solutions used by different actors and different manufacturers. But the idea is to concentrate on the electrochemistry. You can see below the cross-section cell the equivalent electrical circuit. That means that, yes, we can probe and analyze what's going on during degradation. And you can see, for example, typical cyclic thermograms, which are different, of course, because we're using iridium dioxide for oxygen evolution and platinum and carbon on the hydrogen side. The IV curves, which are shown on the right side, I don't know if I can use this. Yeah. So there are two curves here because there is NEPTUNE 117 and 115. And so, of course, the thinner the membrane, the higher the efficiency, which you can see here. So to make this system more efficient, we can either try to reduce the cell voltage at constant cell voltage, and in that case, at constant current density, and in that case, there is an improvement in OPEX. Or you can try to to increase the current density at constant cell voltage, and then there is a capex reduction. But of course, what we're trying to do is to go that way. And the IV curve is very sensitive to different factors, the type of catalyst that you're using, of course, the operating temperature and the operating pressure. And therefore, I mean, this is sensitive, but in some cases, differences are not so big. So if you want to evaluate degradation processes, you have to be careful and to be sure that the temperature and pressure practical conditions are appropriately set and monitored. On the stack, the situation is a bit different. You can see here some data. What we are looking for is homogeneity from one cell to the other. Usually, the stack is operated at constant current density, but of course, depending on the application, there can be fluctuation and dynamics. In that case, this is an example where when it is operated at constant current density, so there are fluctuations, and this is the data that were required for each cell of the stack for approximately 1 hour. So you can see this is what I call a distribution. This is the frequency of occurrence of each voltage. So there is cold water injections. There is water which is pumped into the stack. So there are mechanical aspects with vibrations and so on. And therefore, the information is spread a bit along the voltage axis, and that provides stress, of course. And what is interesting to monitor at stack level is to see the homogeneity. You can see here that there is a temperature gradient. And you can also see here that on the right side that there are some cells which are aging faster than others. And of course, the challenge is, I mean, all these cells are connected in series, and therefore it is necessary to predict, try to identify the weakest one, and try to predict when it will reach a cell voltage which is too high, because in that case you have to stop the resin. So this is a tricky thing. You can have 99% of the cell that works perfectly well, but if there is only one which is out of order, you have to start the stack. And so there are some statistics. We have developed some statistics tools to predict that type of deviation. If we look at durability, I have collected on the left here some literature data, and in the middle some corporate data. So, and on the right side there are some key facts. So PEM electrolyzers are used for operation up to several tens of kilo hours. Of course, that duration depends on the type of power input that you are using. This is where business is at the moment, and there is of course still a need to expand that value up to 100 kilo hours or 120 kilo hours of operation for obvious cost reasons, and this is challenging, of course. And yes, to understand where limitations are and how mitigation measures can be implemented is of course something which is very useful and critical. Oops. So what I want to show this morning is that we can learn a lot from very simple electrochemical analysis using simple 1D electrochemical model. You can see here the very conventional, I would say, equation showing the relationship between the cell voltage here and different operating parameters. So basically we have the thermodynamic contribution, we have internal cell resistances, electronic or ionic. We have charge transfer over voltages and potentially mass transport limitation, which is hidden here in red in some cases. But these are pathological cases, so I don't want to spend too much time on it. And if you use that equation, which is, as I said, basic, because of course it is 1D model, it works well. You can see here on the left some an experimental IV curve. This is a blue symbol, and the fit is fine. And of course, once the fit is obtained, so this is automated fitting procedure. When the fit is obtained, you can split the cell voltage into its different contributing terms, and this is what is plotted here. Just to give you an idea, but I guess this is something which is well known. The different factors contributing to the total cell voltage. So you have first the thermodynamic voltage, you have the oxygen over voltage, you have the ohmic resistance, and you have the hydrogen over voltage. And if you are confident that the model gives you a clear picture of the situation. Then it becomes easy by monitoring and measuring the IV curve on a periodical basis, every week, every 2 weeks, every month, if you want. And then you can analyze it and follow individual cell-contributing factors. And this is what is summarized on this slide. So again, there is a picture of the cross-section. I don't want to enter too much into detail about how we can access, for example, using cyclic photogrammetry, about the concentration of catalytic sites on each side, because that requires some specific analytical techniques. But if we look at the structure of the cell, we can see that we can have different type of aging process. We can have, and this is interesting, even if this is basic, some external ionic contamination. And this can come from process piping or whatever. We can have oxidation of metallic component art interfaces between the people. In that case, we're using a reed as a flow field. So of course, the number of interface that you have in your cell has a direct impact, and the need for coating is questionable. We can lose hydrogen or oxygen active sites, and of course there is a quite fast degradation. We can have some specific membrane or PFSA degradation. We can have some mass transport issues arising, and we can have also when the stack is operated under pressure, deactivation of the hydrogen recombiner, which is used. So again, I don't want to enter too much into details, but for each of these potential degradation process, there is a need to put into action some specific mitigation measures. The management or monitoring of water purity is something which is a bit tricky on large electrolyzer. When you have large volumes of water and you have stainless steel piping and you have different types of process component on the water loops, especially for heat exchange plants and whatsoever. And therefore, the quality of the processed water is something which is very critical. Yes, protective coatings are used, but again, there are so many different types of solutions that I don't want to describe all of them. The loss of electrochemical sites is something which is tricky, and for membrane stability, there are well-known solutions. So I just want to highlight what I'm saying by some AST results, which are summarized on this slide. On the left side, you can see the data, and on the right side, you can see the aging analysis. So this is what we can call an AST, but of course, for R&D purpose, we can always design ASTs of practical interest, trying to stress any type of cell component. But for business, we are more careful because, as I said previously, it's difficult based on AST data to predict the lifetime of the system. And what we want to know is what is the lifetime. And therefore, usually the ASTs which are used are better reflect the power input conditions. So the one which was used in this test, you can see here, this is a simple chronopotentiometric cycle with low current density, so it's not open circuit voltage, smooth amperometric curve here. Then we stay for a given of minutes at 1.2 amp per square centimeter and back down. And you can see here, the top one is the pressure, and then you can see here the stack voltage responses, and you can see here the hydrogen content in oxygen because the experiment was performed at 30 bars. And so there is degradation. And what does degradation mean? It means basically that there is an increase of the cell voltage, individual cell voltage and mean cell voltage, of course. And it goes up, and there is a maximum cell voltage at which you decide to stop the experiment or to stop the system because the energy consumption becomes too high, and then action is needed. So it can be a replacement, it can be whatever to repair maintenance operation. Yeah. And so in that case, we were trying to, and last slide, we were trying to evaluate the impact on this type of AST on the behavior of the hydrogen recombiner. And so you can see here that the cell voltage goes up. And then using the model I showed previously, I calculated the IV curve at beginning of test and end of test. And then I turned this into trying to deconvolute or identify the different factors. So there was a huge, you can see it here on the left, a huge increase of hydrogen into oxygen, which was not due to a degradation of the membrane itself, but to the problem with the recombiner. But there was also an impact in terms of cell impedance and loss of RF. Here is the roughness factor of the oxygen and hydrogen electrodes. So to summarize, when we apply this type of cycle, everything degrades. There is not a specific component which is degrading quicker than the other. And then you have, when you look at the cross-section of the cell, all the factors which are listed here on the left have their own degradation. And therefore, it is necessary to put in place a specific solution to prevent that. It is like a human body. When you get older, everything gets older. It's difficult to have separate there.
Thank you, Pierre.
Yeah. And then there is a list of conclusions and perspectives, and you can look at it. Fully afterwards. Thank you. I try to be as brief as possible.
Questions?
Thank you very much, Pierre, for this interesting presentation. Can you come back to the slide showing the chronopotentiometric analysis?
I just stopped it in order to.
So I understand these polarization fuels have been carried out at ambient pressure, not in pressurized.
No, this is 30 bar. This is the top curve. So you can see here that from time to time the test was stopped and the stack was depressurized. But here this is 30 bar hydrogen, yes.
But
And 15 bar oxygen.
usually at the safety, let's say, approach, we generally, when we have pressurized cells, we avoid, let's say, going towards very low current densities. But high current density, the concentration of hydrogen in oxygen will increase a lot. So approaching the permeability limit. So I was wondering if you decrease the pressure when you move to very low current densities.
No, if you look at the shape of the AST, the time it stayed at a low current density was a few minutes.
Okay.
And maybe it was a bit more than a few minutes. Maybe I think it was 15 minutes at low current density. I have to look over here. Yeah, this is 15 minutes. Then we go up in 10 minutes, and we stay 15 minutes, then go back down, and 15 minutes again. And during that time, there is a recombiner inside.
Okay, you have a combination happening.
So the pressure was kept constant. And there was no significant issue. The only thing is that, and this is what is shown at the bottom curve, there is a continuous increase.
My question is, have you mentioned that the profile of the hydrogen concentration in oxygen, the anode, as function of current density?
Yes. Yeah. And with the recombiner, yes.
Yeah.
Reciprocal versus.
And you are far from the explosion limit at low current.
No, because with the recombiner there is no issue.
Yeah.
The recombiner is active at low current density as well.
Okay, that's clear. That's clear. Is your is made produced by you or by the merchant?
Yes, it was produced by us.
Very nice. You know what is the main degradation mechanism? When I see utilization curves, you see that the sloping this master is like polarizing.
Yeah, so it's a multi-factor degradation process. In that case, you can see that this is what is summarized with this. I tried to summarize it with by giving percentage value. So it's always difficult to discriminate between the membrane behavior and the behavior of metallic components. So what we do is that we perform the experiment at 3 different temperature, and there is a decay with temperature until you can discriminate between the membrane versus the titanium component, in that case, or carbon component. So there was an increase, and I did not specify the type of CCM that we were using, but in that case, it was very low oxygen loading. Very low iridium for oxygen loading. And that means this low, very low means that this is 150 micrograms per centimeter. And so we were trying to figure out what would be the impact of this type of profile, and in combination with interface stress resulting from the current cycling. And yes, in that case, it was aging faster. But there was also an issue on the hydrogen side, and on the hydrogen side, it was a GE. It was so it was not a CCM.
That was one. So it's with no iridium loading.
Yeah, and CCM.
So what we learned is CCS. What we learned in recently at the annex, when they showed that people from the US, that when using low iridium loading, you can increase durability by using an NPL.
No, there is no NPL in that case.
Yeah.
There is no NPL. There is no NPL, and yes, if the iridium dioxide is deposited at the surface of the NPL, maybe in that case, that would be an improvement. But it was basic. It was basic. Let's say fiber PTL.
And what we came conclusion, or let's say the reason is because in low iridium loading, you put more stress if the ports are not closed. So the better to distribute the PTL on the low loading iridium.
Yeah.
That we have.
Yeah. But as I said, the focus here was to test a specific hydrogen recombiner. So it was efficient, but you can see that it was degrading. So there are different things to be investigated.
Pierre, you said something very interesting. So the homogeneity means you used as a standard deviation apart from stack voltage deviation. So the evolution of the standard deviation of the stack voltage.
You mean in at stack level?
And the degradation, the evolution of the degradation in time.
Yeah.
Not only the stack voltage deviation itself, but also the standard deviation of stack voltage deviation.
Yes.
That means you have to measure every cell, right?
Exactly.
Every cell, and if this is feasible for large stack.
Yes. At stack level, it's. I mean, there are technical options to monitor, and it is more than recommended to monitor individual cell voltages on a continuous basis. The problem is that if you don't do that, what you get is a mean cell voltage, and you can have only one cell going up, and even screening. I mean, quite high. I could show some example of cell voltage going up to 3 volts, and then you have transpassivation, and then you have huge contamination. And since the loop, everything is contaminated, so it's a catastrophic situation. So it's better to get by monitoring individuals. So it's not so expensive, and for safety reasons, it's even better too.
Any other question here?
Short one. The influence of pressure, 30 bar, now standard. how do you see that going forward? Should we aim for higher or just go back?
Yeah, so for staff designers, this is a bit of a headache because we are in line with our cell department, and then we have some, please give us a feedback so the stuff we can design.
We can see you now again, but we cannot hear you actually.
Okay. So it should be back on. Sorry for this hiccup. We will try and do maybe 15 minutes.
Yep.
In case we'll get to the lunch break. Maybe one or two presentations can stay after the lunch break. Okay, so and we are 9 now. So the ideas. Okay, let me share screen. Yeah. We try it.
Great. Hello, everybody, and thanks for the opportunity to present. After following Professor Millet, I feel this presentation is a little bit lightweight compared to the good data presented. But take into account, SCHAEFFLER has started the business unit 3 years ago, and if it takes 2 years to order a test station and install it, the durability data will not be that long. So SCHAEFFLER as a company has a strong reputation in ball bearings, so it's a metal company. We are in deep down south with the headquarters of Germany, where we have a strong commitment for renewing our direction and focus in mobility. And this concerns e-mobility, this concerns fuel cells, but also making hydrogen. So I feel very strong backing from our board level. And I don't think this is only a hype. We are in to stay for longer. As you can just see here, we're a very big multinational company, about 80,000 employees worldwide, and we have a huge turnover. So I'm happy to be in this company directing them towards electrolyzer hydrogen production.
This is a quite important slide for us because it shows the vision. We make ball bearings not just for cars, but also for the windmill industry, also for the London Eye for that case. But we see this as a huge market picking up from megawatt to 15, 16 megawatt and not stopping there. So the wind to hydrogen is one of our main visions. You can see in green here, the electrolyzer is a key point in the conversion of energy. But hydrogen is not the goal. The goal is beyond that. It's the industry, the transport, heating, and green steel. And mind you, we use a lot of steel, so it's in our own interest to show how we can make that greener. To be exact, we use about 1.1 million ton of steel. So making all of that green won't happen overnight, but hydrogen is going to be a key reducing agent. It's going to be a key fuel cell, a fuel carrier, and we are very convinced about that. So you can see we're in here for the long run, and we want to use our competence. We see from our side PEM having a unique advantage of being very dynamic. We can follow the source, we can follow the consumer, and we can deliver at pressure. So here's some of the good work done by the Hydrogen Europe in the past, estimating the size of the market, which is huge, and the amount of PEM that will be part of this share. Here it's estimated at 30. Here on the Asian side of the world, it could be 50, but it's definitely here to stay as long as we can get the cost down. So I'm going a bit more into detail now. Here you can see what our company has done so far. The Hanover Messe showed a lot of nice shiny metal plates. In the background, you can see a large plate, which is not necessarily useful, but it shows what we could do in the flow distribution within this bipolar plate. You can also see a fuel cell equivalent, but the translation between is not one-on-one. But we do have in our automotive side a 100 kilowatt stack with metal plates, and we have on the other side, the industrial side, where I am, a megawatt stack to launch into the market and see how this works. The key feature we want to achieve is we want to replace titanium with stainless steel. We have coatings that work for bearings for a long lifetime. We see the operation window could fit. So this would be able to get some of these more difficult materials out, but also enable us to form the flow structures. We don't need the metal in there. We need an open flow channel structure to evenly divide the activity. And then it's the question, what's the optimum active area? Is that 5,000 square centimeters, or should we go to a smaller area and use tight tolerances to stack up to a higher voltage, like 200 cells or 400 for some fuel cells? So as shown, the key parallel that we see is there is a tolerance issue with stacking the plates. This is something where SCHAEFFLER has a lot of experience with industrializing, and we also want to include the seal on the bipolar plate. This means we can adjust the PTL height and the tolerance of the seal to exactly what you need. Since most of us are using pure water for electrolyzers, or maybe 1 molar kWh for AEM, getting an optimized flow distribution should be quite standard. So the ultimate goal in our MIC team is to achieve standardization, like with the fuel cell. That means it should work. And I've been in the hydrogen business long enough to know we need cheap hydrogen. Otherwise, we'll always be looking for funding from our governments. So it literally translates to your working point on your IV curve. Here I've plotted 3 different lines, the red one being the standard Nafion 117 type, a vintage membrane, as some people call it, but it's long and everlasting. Jumping to a thinner membrane in the blue line, Nafion 115 type, that's already ongoing. And people are saying we can stretch that curve to higher current densities. And I always smile when people want to go to 3 amps per square centimeter. Like 20 is here, 2 amps per square centimeter. But if we extend that to 40 or 50, you get to a voltage that is not economically viable anymore. It's too costly. More important for us, the coating we put on the bipolar plates of stainless steel also have a certain level where they're stable, and above 2.4 volts, we need to go back to precious metal again. So the degradation processes that we're monitoring now have a strong effect on, do we have an influence of our plates? We have entered the shared research program with TNO to validate that in the fields by external parties, but we also see the need to reduce the voltage further. So this new green line is typically what comes into the market as thinner membranes, new catalyst formulations, so we can stay well under 2 volts. But this is very important for our degradation monitoring. So moving forward, what I need to do in our team, we have now about 30 people in our R&D team, is we have to work on the right thing. So we need to understand what the problem is and find a material solution. We don't do systems, so we can't find a workaround with more flushing, better quality water, or thermal strategy. We need to make sure that the hardware we put in is long and everlasting, is durable, is fitting, and doesn't allow leakage of hydrogen. We mentioned direct injection into the pipeline. Wind to hydrogen and into a pipeline would be the perfect scenario. So we have thick plates. Why not put a seal on there that can hold 100 bar? If people need it or not is then a choice of our customer, but the plates will not get thinner. We will design it in a way that we can hold this pressure and anybody can put the wrong CCM on the inside with the adjusted measures accordingly. What we are also doing is we're using this 01D model to predict the ideal stack in any location in the world. So we're monitoring the renewable energy. We're looking at how much current we are pushing into the stack and how much heat we have to take out. This has implications for which PTO we use, which catalyst we use, and what type of flow we need. What is unique to the SCHAEFFLER stack is we have a separate cooling loop, just like a fuel cell. And internally, we are strongly debating, do we need a separate thermal cycle? It could help control. It could also help avoid any contamination of your catalyst if you have to flush 3,000 liters per minute through the anode side. So we are investigating this through modeling and through testing. And in all honesty, the testing is only just starting. We'll have 1 megawatt running in our headquarters in Schweinfurt continuously, but we will learn what it takes for energy, what the cost is, and what the problems are. Also, maybe interesting to note, we put all of our data into the cloud immediately, internal, external, all the same. And we don't use Excel anymore, that's rather limiting. We use the Grafana tool to analyze retrospectively what's happening. And I hope very soon we can disclose some of that data and open to the public. Through TNO, we have one of these stacks also running. That will help not just R&D, but the whole community. So we have a range, thanks to the purchase of the company Hydron, active in the field in Holland on a small scale. The screeners on the left-hand side are available to everybody. Buy them, they're good, but they're not the only ones. What is very interesting for me is to see how does the behavior, the performance, the degradation on a small scale screener cell compare to the larger stacks. As mentioned, the megawatt stack behaves a little bit differently. And the 100 kilowatt stack that we are now actively making and pushing to the field, not every stack is similar. I get a lot of questions, well, what's the problem then? And then I look into my glass ball and I have to guess what it is. But without the data, we're going blind. So getting that data is key, making that available and sharing the learning. As mentioned, do we need an MPL on the PTO? That's a key question everybody can benefit from. And we have already seen that our PTL supplier base needs to be educated. There's a strong influence, and we're characterizing that now. So looking to the future, a 1 megawatt stack is actually too small. If you put that in a container, you don't really have a winning business case. So either you stick smaller or you have a series of them. So we will have stacks that are series connected. So we have 10 megawatt or 20 megawatt blocks. Now, how should we configure that stack that is most cost effective for the system? We're working on that. We're listening. I would like to welcome other people to join that conversation, because if we want to win the hydrogen race, we need cheap hydrogen. And that doesn't mean gold-coated plates of a certain thickness and everything. So we called it a SCHAEFFLER stack, but that's more of an intern terminology before we get a sexy marketing name for it. So I'd like to close with this slide. There will be PEM, but there's also alkaline, there's also storage. I'm still looking for this ideal stack size. We need to have a width that matches roll-to-roll manufacturing. We need to have an active area that matches the power supplies that are in a sweet spot. And I'd like to know from the market, do we really need 4 or 5 amps per square centimeter, or is there a dynamic protocol that I can follow and expect to run with the customer? It's work in progress. I haven't spoken to somebody with the ultimate answer, but there's been companies in this field that have pushed products that are becoming kind of the reference. So it's an open spot. Low cost of hydrogen, low cost of ownership is most important. And for SCHAEFFLER as a company, we make quality. So we want customers to be able to rely on us for their business case to work. I don't expect stacks to run until failure in the field. I expect them to run until the business case doesn't work. We watch it in the field. We have the monitoring. And when it doesn't work, we recycle. So a lot of our activities is not just making the stack and selling it off and saying, until later. No, the stack will come back. So we need the degradation process monitoring to know how we can recycle the materials, especially if we make green steel bipolar plates. I just want to give them new coating and send them back out. I don't need to completely start the loop all over. So not so much degradation data for you to learn from, but just know that we have got our test field up and running. We have got the Internet of Things going to measure with customers the latest materials, how they behave. And very soon, I hope to tell you what the customers really need or what hydrogen is. With that, I'd like to close.
Other question here?
I was wondering, you mentioned tolerance and thin membranes. Do you see a challenge there? We're obviously going for thinner membranes for lower rolling distances. Are we getting a range which is hard to get to tolerate?
Well, I would say the membrane always fails first. So the CCM will get the blame for failing. And some of the CCM suppliers may find that indeed they're always on the pointy end of the stick. Knowing that we need a very soft, smooth mattress without stress points, thermal stress, mechanical stress, chemical stress, we will push the limit. My feeling is a 50 micron membrane may be the sweet spot. And in the past, I've measured, you can put 1000 bar pressure on a 50 micron membrane. However, doing that in a stack level with production tolerances, with not every stack being the same, that's where I see a huge challenge, where not just a robot can do it. We need to understand what we put together and how we assemble it. Luckily, the fuel cell community has already experimented with 8 micron membranes, really thin, So we have some experience. We can piggyback on it. The key point, I think, will be this back diffusion of hydrogen, making radicals, not just the main reaction of making hydrogen and oxygen. It's the reaction beyond that, the parasitic reactions, the black art where your anti-degradation mechanisms, that's where we can hopefully achieve 80,000 hours.
Thank you very much, Peter, for your interesting presentation. Regarding the cost of green hydrogen at the moment, the impact of renewable energy, you know, very well, it's at the moment phenomenal compared to the capex. Of course, in your efforts to change the thermal state will have a large impact in the future when we expect that the cost of renewable electricity will decrease significantly and the impact of capex will increase. But of course, we also need to protest the precious metal. Precious metals, a high loading on precious metals in fact, that is another aspect that could be also dominant. So we need to understand which kind of scenarios that we will have in the future and what kind of innovation we need to address in order to anticipate these situations and try to get something that they could be, you know, competitive in the green hydrogen market.
I think it's an excellent example of how we need to think beyond what we can just make and hammer out. If I ask my models now, any location in the North Sea will generate hydrogen at a cost of 4 to 5 euros per kilogram based on wind energy and electricity. That's too high. So either we utilize more business cases of making oxygen useful, grid stabilization, etc., or we all wait for that one peak of cheap energy. In anticipation of this, we have put our heads together and succeeded in getting the Heracles AEM project funded from the EU. So we will use one of our 100 kilowatt stacks, the one you see in the picture here, and convert it to AEM with the learnings of all the projects so far. This will be one stack. So if it works, I hope to show the world and SCHAEFFLER internally what it means to roll out an AEM version with low capex and compare it directly with PEM. I'm sure there's a business case. We will use the numbers accordingly. But for now, the polymers of the AEM, which are the most critical factor, is not in the competence area of SCHAEFFLER being a metal company. So I'm very happy to do this in a consortium and contribute our expertise. And let's make it work.
That's another question regarding the membrane stability that is relevant to this workshop. Of course, there are a lot of efforts in trying to implement the radical scavengers inside the membrane that can extend the lifetime of the membrane by, you know, addressing these significant degradation mechanisms. Of course, that it should be, in my opinion, also what we need is a similar efforts also for the catalytic layer, because we have also the degradation of the ions inside the catalytic layer. But we would like to mention also about Pierre that, you know, the use of the recognition catalyst can reduce the hydrogen content in oxygen, so allowing it to stay in a safe side. Also, the radical scavengers, it would be also a good option to increase the standard membrane and ion lifetime, and this could be, let's say, very useful to make these systems more reliable in the future.
Yes.
So I have two questions. The degradation monitoring, voltage, stack voltage, cell voltage 5. Anything else? My first question. And the second question, if you have a system which has more than one stack, say more than one 10 or 20 megawatt stack, how you would operate the other stacks? Would you have just a kind of base load or a couple of stacks and sacrifice one stack or two stacks for taking the highest load?
Both good questions. Cell voltage monitoring in a fuel cell has always been under discussion. Most automotive people said, throw it out, cost, we don't need it, you should just put it. In the electrolyzer stack, we have a more expensive unit, it's justified. And actually, it's not developed far enough. I want to monitor the temperature profiles. I want to measure the CDM at 2 or 3 places on a singular cell. I want to measure the water quality, and there may be 2 or 3 other things we can easily plug into even a standard iPhone that we deliver with the stack. So the measuring is not the problem. The computing power also not. We have enough data in the field, but we need to find a system that is cost effective in streaming the right amount of data into the cloud and allow health monitoring. With a health monitor, we can monitor a series of stacks. Indeed, I'd like to have stacks working at their own working point. Some accelerating a little bit because they're older anyway and we'll replace them in 2 months. Or some taking the efficiently base load. But this is very much depending on your power configuration. I'm very keen now to understand the sweet spot of the power supply, but also if we can use an active front end type IGBT to have multiple stacks at different working points. I can do dynamics, yes, but if the system can't, then I'm still stuck to one working point and competing with Alkaline. So this power electronics connection and how we put this array of stacks together is going to be the key to make the 20 megawatt system work.
Okay. Thanks. We have no question in the chat.
No.
No, then we can go to the next. Thanks.
Ah, sorry, no, there is a question.
Yeah, there's a question.
Coming back for you.
Yeah,
ahead.
thanks a lot. I think you answered it already a bit, but yeah, just coming back to the EU harmonized AST tests. So from your perspective, so mainly from industry perspective, what would be additional info or tests which you would like to see in the test behavior?
What I need is to have an element of the test protocol that is a universal standard, a reference that I can share and that people recognize and can agree to. I need the internal test facilities in our company and outside of our company to be aligned. There is a lot of discussion on which protocol makes your product looks the best because you want to sell as a business. But because we are looking beyond just the sale, we want to take risk away from customers. We need to guarantee performance and lifetime at some point. And this is now impossible. Customers ask, but subject to so many things, nobody wants to do it. Through harmonized testing, we can measure progress, we can measure quality, we can literally baseline ourselves. And that's why it's so important to have a public standard that we can use and implement. Whatever comes on top as a proprietary protocol is then in addition.
Thank you.
One more question.
Cycling of these tags. So I just have a question. Did you already start doing it? And if yes, like which component do you think is most difficult to recycle? Because like membranes, we know that they do degrade and it's very difficult. Like that's the most non-degradable thing. But we would like to have that recycled. So what do you think on that?
Well, having worked at Johnson Matthey sometime, the PGMs is the easiest. I am more worried about the fluorine indeed being discussed. I think the answer will be we need to make sure nothing gets in the environment. So the FKM rubbers that we are using, the Teflon coating on GDL components and even the ionomers and membranes, yeah, we don't want to just burn it up. We need to find a way to bring it back in. I have the feeling that separating the catalyst from the membrane again, with platinum particles everywhere, cannot use solvents. That's a fire issue. So we need to find a way to split them and separate the ionomer molecular weight profiles to the good polymers and the chopped up ones. And that's a key missing spot. People don't know how to use old membrane snippets yet, but it will have to be a full cycle because fluoropolymers, I think, will be in short supply. And from the SCHAEFFLER standard point, stainless steel, we recycle bearings all the time. That's something we can handle, but it needs to be done.
Okay, so we go to the next presentation. Frédéric, good.
Hello?
Yes, we can hear you.
Maybe I can share my screen?
Yes.
Okay. Is everyone can see my screen?
Yes, we can see it.
Okay. So thank you for giving me the opportunity to talk about some protocol we are used in NEWELY project. My name is Frédéric Fouda-Onana from CA Lytton in Grenoble. Maybe, sorry, I can add the camera. So yeah, my talk today will be mainly on protocol rather than, raw data that we have obtained in the NEWELY project. And I just briefly recap here the main outline that will be discussed during my talk, which is a break-in protocol, IV curve measurement, influence of the flow rate, impact of the cell resistance, and the short conclusion. I also want to highlight that for all the results that will be presented here, the same testing condition were used, which is 50 degrees C, 0.1 molar kWh, 1 bar, and dry cathode mode. So first, once we insert the MEA in the cell, there is a break-in period protocol. That I want to highlight on this figure on the left side is the protocol was consist firstly to a manual fast breaking by increasing the voltage from 1.3 volt to about 2.2 volt with a step size about a few minutes in the range of 1 minute. And what is interesting to show here, it's below 2 volt, the current didn't increase, but it starts.
Sorry, can you hear me? At least for me, the slides aren't moving on.
Now I'm on slide 3.
Yeah, all I can see is the title slide. I don't know if that's the same for everybody else, but that's all I can see.
Exactly.
Like that is better?
Yes, that's better. Now we're on slide 3. I don't know what slide 2 was, but now we're on slide 3. Thank you.
Okay. So yeah, that my talk here was to say below 2 volt, we don't see any increase of the current, so there is no activation of the cell. But once we go higher above 2 volt, for example, 2.1 volt, we can clearly see an increase of the current, which is become even higher when the voltage goes higher. And of course, when you back to a lower voltage, you still have an increase of the current. So the cell is properly activated. So what's happened on the electrode during this break-in period? So there is a small decrease of the high frequency resistance here, but the much a drastic difference is on the impedance in low frequency range. You can see here in the open circle that the resistance at low frequency is much lower than the value before the break-in. So the break-in had a more important effect on the electrode, and that effect appears when the voltage is above 2 volts. So then here it's the common protocol that we have used for our testing. So as you can see here, after 5 cycles, there is no big increase anymore of the current. And if you see the IV curve on the right side of the slide, you see how big is the impact of the breaking period, since you can gain about 400 millivolt at 1 amp per square centimeters before and after the breaking. Then another topic I wanted to discuss was about the IV curve protocol. So in the document disseminated by GRC, there is a protocol to measure the IV curve by maintaining the current density for a given period of time, and to measure it in the forward and backward sweep. As you can see here on the IV curve on the top here, there is no so big difference between forward and backward IV curve. There is less than 30 millivolt difference at 1 amp per square centimeters. And when we measure it with the potential dynamic mode, here the scan rate was 5 millivolt. There is a slight lower performances between the potential dynamic mode and galvanostatic mode. We think that this difference could come from maybe a slight increase of temperature during the galvanostatic mode measurement, since we stay at the same current for a much longer period of time, so the cell may warm up a bit. That could increase the transport of ion through the membrane and also improve a bit the kinetics. But in both cases, either potential dynamic or galvanostatic, we didn't observe a large difference between the forward and backward IV curve measurement. Then another parameter was important to, let's say, to investigate what the impact of the flow rate. On the curve on the left side, you see the impact of the flow rate at 2 volts when the cell was maintained as 2 volts. So initially it was 10 milliliters per minute, and then we increased the flow rate to 30, then 50 and 80 milliliters per minute, and we see a slight decrease of the current density when the flow rate was increased. And if we decrease again the flow rate, we saw an increase of the current density. So it seemed that reducing the flow rate could improve the performance. However, during the IV curve measurement, that effect was not observed. So I saw in the previous presentation on AEM that it was better to increase the flow rate for the stack, for example. But here, I mean, it was maybe something to discuss, because here we observe that reducing the flow rate seems to improve the performance. Then another topic that I wanted to discuss is the importance of the cell resistance before measuring the IV curve. So as it was presented by Frédéric previously, so here's a picture of the propulsed cell in which there are some pole plates to recover the current. And the idea here was to measure the cell resistance before inserting an MEA inside. So we made a lot of tests. So we tried with titanium foil, carbon-coated stainless foil, and stainless steel foil. And so what we can see is the stainless foil that we had at the beginning was gave a really high value of cell resistance, about 740 milliohm square centimeters, which is not usable in the cell. In comparison with the titanium foil or carbon-coated stainless steel foil, where the value of the resistance was in the range of 200 milliohm square centimeters. So this stressed the point that before inserting the MEA in the cell and to be able to compare with some other results, it could be really valuable to have the value of the cell resistance to be able to compare with some other results. So when we see the impact of the foil in the MEA IV curve, we see, for example, when we replace stainless steel with titanium foil, we can gain 170 millivolt at 1 amp square centimeters. then when we see on the impedance spectroscopy at two different voltage, 1.5 volt and 2 volt, we see that the main impact is at the high frequency resistance, where we can see 200 milliohm square centimeters that we can see at 1.5 volt, and we can also see it at the impedance at 2 volt. And the last, let's say, evidence of the large impact of the cell resistance is the difference of the voltage at different current density. So, for example, from 200 milliamp per square centimeters to 1 ampere per square centimeters, I measure the voltage difference between the two curves, and we can have a nice straight line, which is shown again that the cell resistance was the main cause of the difference between the value of the titanium foil and the value with the stainless steel foil. So when we put a gold-coated stainless steel foil in between the two plates, we can have a 46 milliohm square centimeters. So which is I think a good value to say the cell is working properly. So again, I think that to have this value, to be able to compare a result between different labs or between different partners, it will be relevant to have this value. So as a conclusion, just to recap, so the break-in protocol in our test showed that below 2 volts, we cannot have any activation of the cell. We don't see any increase of the current. And probably the break-in period could not be harmonized because it may depend on the cell or something, the catalyst also that was in the MEA. For the IV curve measurement, we didn't see any difference between forward and backward scan, either for the galvanostatic or potentiodynamic mode. We also observed that there is the influence of the flow rate. It seems that reducing the flow rate seems to increase the performances. And at last, I think that the impact of the cell resistance on performance is for sure very huge. And maybe to have a value of this, to be able to compare a result between different labs or between different partners could help to have a better comparison between results. So thanks for your attention. I want to thank my colleague at CA and also all the partners of a NEWELY project. Thank you.
Any questions from the room? We have a question in the chat. Can you see that?
So the question is, do I think that the break-in at a voltage higher than 2 volt can negatively impact the stability of the MEA cell component? Yeah, I mean, I think that to go above 2 volt could make some passivation layer, but the point is this break-in period is not long enough, I think, to grow a thick passivation layer on the current collector or on the catalyst. So I'm not sure that it may impact negatively the stability as long as the break-in period is much lower than the aging. But yeah, of course, there is also a limit. I think above, let's say above 2.2 volt is too high.
Yeah, second question in the chat.
Did you try looking at the minimum activation potential as function of KOH concentration? No, I didn't try that. So I don't know.
I have a question to you. Since in the AST protocol report, we recommend the polarization curve measurements to determine the stack deviation. Do you have any recommendation how to improve the procedure JSC will report on the polarization curve, this procedure?
Again, the procedure on AST?
The AST protocols will make reference to the JSC for the curve measurements test procedure for low temperature electrolyzer. Do you have any recommendation? If you don't have them now, please write to me because I will have to refer to that. As regards the time, you said there is can be some heating in the stage when the current is kept constant, or up and down, or backward, and so on.
Okay. But this is, I mean, it's assumption. The main assumption that I have to explain why between the potential dynamic mode and the galvanostatic mode, there is a slight difference in the Harvey curve. I mean, my main assumption is maybe the cell may warm up a bit, and so kinetics and transport of ion may be increased, may be faster, and so the Harvey curve is a bit better.
So would you recommend the galvanostatic measurements or the potentiostatic measurements?
Galvanostatic, because you have a better, I think, behavior of your cell at a constant current. And also, I think again, sorry.
You will also have forward and backward as both measured.
Yeah, but as you see, there were no big difference between forward and backward. So for me, it's there were no big impact on that. Also, yeah, there's another problem maybe because this test was performed at atmospheric pressure. So maybe it could be more difficult to go in backward direction if you are under pressure, because when you will reduce the current density, you may have a much more hydrogen permeation, and it could be probably some safety issue.
Okay, thanks. Other questions?
There was another one in the chat. My metallurgy is poor, but I recall that TE dissolved in KOH at higher potential. Is that what's making the TE look better? So again, in the test using titanium, the titanium was to replace the MEA. So there was no KOH flowing in the cell. There was no electrolyte in the cell. The idea is to measure the electronic cell resistance. So there will no matter of any dissolution of titanium or any impact of KOH. So here is just to measure the cell resistance with any metallic sheet to replace the MEA.
Okay, thank you.
Thank you.
We go to the next presentation. Okay. Alkaline. Sarah.
Okay, so hello, I'm Laura Abadía. I work at the Aragón Hydrogen Foundation, and I am the coordinator of the hydrogen production and storage area, and also the technical coordinator of the project HYPRAEL. I will start my presentation giving just a very brief introduction or notions about our entity. Next, I will talk about the HYPRAEL project, a project that has started this year. And I will continue with the experience that the Foundation has in accelerated stress tests. So Aragón Hydrogen Foundation is a private non-profit research and technological development center created to promote the use of hydrogen as an energy vector. We are placed in Huesca, Aragón, and our facilities include offices, laboratory, and a workshop. We have around 1,000 square meters of surface. So we can say that our unit is quite unique in Spain because our workshop has around 8 meters in height, also safety measures, gas detection, and equipment and ventilation. So it's a good environment to test hydrogen equipment in medium and in big scale. Aragón Hydrogen Foundation was created in 2003 by the government of Aragón with the support of several companies and institutions. And now this support over these 20 years have become bigger. And now we count with a board of 88 partners or entities. Within the technical area, we are several departments. We are the R&D department, the innovation department, and the consultancy and training department. This slide is about the R&D department, which is the department which I belong. And in this department, we focus, or the project that we work on focuses in bringing technology on tier R from 3 to 6. We validate proof of concepts. We validate also novel technologies, and we carry out tests under relevant environments. Here you can see 2 images of 2 photos. One is of our alkaline electrolysis test bench that is going to be used in the HYPRAEL project. And the other one is the testing platform that we have is being used within the project HIGS that is about hydrogen injection into the natural gas. In addition to that, we have other projects about other topics, metrology of renewable gases, use of hydrogen, production of alternative fuels. No, but well, now I will talk about the HYPRAEL project, which is the alkaline electrolysis project. So HYPRAEL project its title is Advanced Alkaline Electrolysis Technology for Pressurized Hydrogen Production with Potential for Near Zero Energy Loss. It started this year in March, has a duration of 3 years, and the Clean Hydrogen Joint Undertaking is the entity funding the project. And well, the foundation, Aragón Hydrogen Foundation, is the coordinator of the project, and here you can see the rest of the partners involved. They are Solvay, Beko, ACFA, Fraunhofer, and Green Hydrogen Systems. Well, this project focuses on developing an advanced technology for energy and cost-efficient compressed hydrogen production. The main goal is to develop and validate this next generation of alkaline electrolysis for highly pressurized hydrogen production. We are aiming to reach 80 bars or even beyond that. And we plan to accomplish through several key innovations that involve advanced cell, stacks, and balance of plant. And of course, it's going to be necessary to do research on advanced and sustainable electrodes, separators, but also its polymer and its compositions. And we also plan to evaluate scaling in order to help to aiming to sustainable mass production. So the project has several key research activities, as I was saying, material development, but also their screening,
This is going to be done at lab scale or single cell by the partners Fraunhofer and Afron. The most promising candidates will be upscale and will be included in a stack that will be validated at pilot scale at the test bench that I showed you before. And here we plan to reach up to 60 bar, about 100 Celsius degree temperature, and the stack will have a power of around 10 kilowatts, let's say. And this activity will be done by the Foundation with collaboration of partners, but leading by the Foundation. And also the best candidates, or the ones that work better, will be again upscale at industrial scale, and they will be demonstrated. And in this phase, the pressure will should be, or we plan to be, higher than 80 bar. Temperature will also be increased a little bit more, and the stack will have a power of more than 50 kilowatts. And this task will be led by Green Hydrogen Systems. However, the project has started this year, so all these phases about this validation at the scale, at stack level, will start next year. We plan to start it in August next year. But so far, well, we have already talked a little bit about what kind of tests we plan to do, or at least what we want to see. So we plan to investigate the effect of electrolyte concentration, temperature, and pressure. For that, we will base on the harmonized protocols available. And of course, we also will consider, or will base in other projects, and even our own experience, because we also led the integration project and participate in the QualiGrids project. The test in this scale include 2 rounds of testing, 2 stacks, one that will include components, state-of-art components, and the other one that will include the advanced component developed within the project. And well, each stack should be under testing around 3 months. So we are considering that we will do accelerated tests to analyze the performance. Okay, now this graph, or what I will go to explain, is more related to the integration project, a project that was also funded by the Fuel Cell and Hydrogen Joint Undertaking just 3 years ago. It finished 3 years ago. And well, in that project, what we also testing several stacks, and we designed our own accelerated stress test, because at that moment we didn't find protocols, or we didn't find protocols to test otherwise. A reference that we found was about accelerating stress tests, but for PEM fuel cells, not for electrolysis. And we try to extract information to understand the methodology that they applied, and then we develop our own protocols. However, when we receive the stack, we carry out 2 kind of testing. Let's say we started with a characterization test at different KOH flows, temperature, pressure, in order to characterize the stack, to identify its operating windows. And we did that based on the cell voltage that we measure and the gas purity that we obtained. Once we have this characterization, then we move on to the accelerated stress test. At this AST, we started with a polarization curve as beginning of test, and after the AST was finished, we carry out another polarization curve. And well, the results that we obtain graph like this one, where we could see that every time that the AST consists on several cycles that repeat different times or a number of times, and we observe at every iteration how the cell voltage changes and how gas purity also changes. So our conclusion at that moment was that for one of the stack, and this conclusion is not for the 5 of them that we tested, but some of the conclusions were that after 60 days of dynamic operation, some of the cells presented a higher increase in the cell voltage than the other ones. Some of them even increased 12% of degradation, right? Let's say, while others only 2-3%. And we also observed that gas purity did not change did not change over time, even if the operating condition was 25 bars. And in addition to this, we learned several lessons. One of them, maybe the most important from my point of view, is that the thermal management of the stack is very challenging for high current density variation. So our IST, the idea was that only current density should change. Pressure and temperature needs to keep constant. However, when we perform this high variation in the current density, there was always a little small period of time where temperature increased, and this was done. Though this happened at every time that this current density variation happened, every cycle. So in the end, it's like, I understand on my point of view, is that it's like a hidden stressor, because temperature should be kept constant, and we were not able to really get that. Another things also is that our AST had a duration of 1 week, because for time constraints, because we need to test several stacks of how the project went, and maybe 1 week of this accelerated stress test was little, even more knowing that what is said in the GRC documents and in the other projects. And yes, and I think that's everything. So yeah, thank you for your attention.
Question in the room? Thanks for the presentation. Do you see any correlation between degradation rate and cell position in the stack?
Yeah, I understand. I see your point. However, for our case, it was not so simple, let's say, because every stack that we tested had different components. Some of them contained new electrodes, while other was were the membranes, the one new. So I know that voltage, or this increase in voltage happened more in some of the cells, but right now I don't remember which one of them. But it's something that yes, it happened. Yes.
Which type of SCHAEFFLER did you use?
The standard one. I mean, Zirfon. Yeah.
Yeah.
Ulrich?
Okay, thank you, Laura. So I think for the AST, it's also important to keep the pH concentration constant. How do you do that? Maybe contact letter with the high pressure.
Okay, yeah, the only condition that we wanted to modify was the current density. All the rest, we try to keep it constant. So KOH flow was also that we kept constant. Yeah, we recirculate the electrolyte with a pump, so I don't think we do anything more difficult than that. So maybe I don't understand your question right.
But do you monitor the KOH concentration in your gas, sorry, in your circuit?
Okay, we take several samples, but not continuous measurements. And within that sample, we measure the density of the solution. And during the time that the test, during this week, we didn't observe a variation. But maybe, maybe it happens if you test for more time, or you need a more precise measurement to see really the changes. Okay, so Ana Maria, at which scale was the protocol you described performed? We did this protocol at pilot scale with an stack around 6 kilowatts, I think. When looking at the cell degradation, did you contact the bipolar plates or the electrode directly? Yeah, we had a device connected to each of the cells or in contact with each of the cells. So we measure cell voltage of every one of them. And also, I mean, we have this measure always, but the AST has had a small period, always at the same current density, where that allow us to monitor the evolution at that moment. And also we compare the polarization curve before and after the AST. But we did that during the test, so the system was running normally. It was not in a separate test. What was the rate of current run between two different load points? I need to check that. Right now, I don't remember, but I can check it. And if you want to send me an email, my email address was in the presentation, then I will contact you back. What kind of thermal management did you use, internal or external to the stack? Well, KOH solution is the fluid managing the thermal stability of the stack, and this KOH solution also was in contact with our cooling system, a solution of ethylene glycol. So I don't know if that answers your question to see is internal or external.
Okay, thank you. We will continue with the next three presentation after lunch. Lunch will resume here at 2:00.
Session is.
The session is resumed, yes. So.
This is great.
Mike.
Yeah, but
So you should be there. The camera there. Does it work? Okay, I'll do like this. I'll page down. It's not perfect.
Not mine.
And also do it with
Move okay with these.
you can move 2 fingers. 2 fingers. Oops. Wait.
No?
Wait, because now it lost connection to the. Okay. Fine. We're on that.
Slowly, I just have to. Please, yes, one touch with for.
Or with 2 fingers.
Yeah. We can no to include all pages.
It's the format, I think, of your page. It's a bit old-fashioned. Should use a. Okay, it was a pleasure meeting you.
So we continue with the next 3 talks. Stefania?
Thank you. Good afternoon, everybody. My name is Stefania Siracusano. I'm senior researcher at the CNR Institute of Advanced Energy Technology, Nicola Giordano, in Messina, Italy. And I'm going to talk about accelerated stress tests in proton chain membrane electrolysis. This activity is included in the NEPTUNE project. It was an Horizon 2020 project that started in 2018 and concluded last year in April. Next generation of proton chain membrane electrolyzer under new extreme. The main objective of this project was develop a set of vector solution regarding the component, stack, and the system in order to arrive to 100 bar and reach also the current density, work at the current density of 4 ampere per square centimeter and maintain the energy consumption less of 50 kilowatt hour per kilogram of the hydrogen produced. The aim of this project was to bring this new technology to TREL 5. The similar activity, including this in this project, was regarding the analysis of the performance degradation during the durability test in steady state and low thermal cycle in single cell. And on the left, you can see the electrochemical characterization at the beginning of life of the MEA tested, polarization curve and impedance spectroscopy at 1.5 and 1.8 volts. We have reached at the beginning of life at 3 ampere per square centimeter the cell voltage of 1.82 volts, and the voltage efficiency was 81. On the right, you can see the protocol used for this test. We have used for the durability test in steady state, work at 80 degrees, and for 200-hour test at 1 ampere per square centimeter, and after that switch at 3 ampere per square centimeter for other 800-hour test. For the test and load cycle, we use different cycle for different cycle. We started with the steady state for the condition for 20-hour test at 1 ampere, after a switch at 3 ampere, and started the first cycle from 0.2 to 3 ampere per square centimeter. in the medium frequency, we recorded 9,000 cycle in 50-hour test. The second cycle was carried out, switch on off the current density from 0 to 3 ampere per square centimeter with the same frequency, 9,000 cycle for 50-hour test. The third cycle was carried out at high frequency. We recorded 45,000 cycle in a 50-hour test. And the last one was carried out with the low frequency, which every 30 minutes we recorded the point, the cycle. Okay. This activity was carried out with the low catalyst loading included in the BA. We worked with the 0.1 milligram per square centimeter for the platinum and 0.4 for the iridium ruthenium electrocatalyst synthesized at CNR. This is the results for the durability tests carried out in steady state. As you can observe, the increase of the potential value at both current density, up to 1 ampere and 3 ampere. This is probably due to the immediately switch on the current density from 0 to 1 and 3, but also the probably the thinning of the membrane or cleaning of the membrane at the first period of the steady state test. We have, in fact, recorded the degradation rate, 90 microvolt per hour for all tests, but this degradation decreased in the last period, as reported here at the last 300 hour test. We have reduced at 33 microvolts per hour. We have observed also the reversible loss that is associated to mass transportation. This is due to the presence or the change of the state, the oxidation state of the anode side, but also is probably due to accumulation of the gas in the cathode, in the anode side, and create a barrier to give the gas to escape from this catalytic layer. This is called the supersaturation of diffused gas in the catalyst layer that provoke this mass transportation. These reversible laws are more evident in the second durability test in this. Okay. This is the results for the low cycle durability test. In blue are reported the current density that we have applied, and in orange you can observe the different cycle. It is evident that during the period of the steady state of this test, we have a decrease of the performance, as you can see here, 20 hours, here 100 hours, here, and so on. Whereas during the period of the cycle, the load cycle, we have observed lower decay. As you can see here, is more stable here compared to the period of the stability, the stability test. This is due to the presence of this recoverable loss. And when we switch at high and low current density, we reduce this recovery loss, and we have a partially recover of this reversible degradation. This means that at the lower reversible cell degradation is therefore foreseen during the cycle operation compared to the steady state operation. After the load cycle, the same MEA was subjected to the load and thermal cycle. Here reported the graph. This means that we have switched the cell, the MEA, from room temperature 18 degree, or switch from 3 ampere per square centimeter to 1 or 0. in order to see the effect also the combined load and thermal cycle. We don't observe different after this load and thermal cycle, as reported in the table. We have 95 microvolts per hour of the degradation rate for the load cycle presented in the last slide, and 0 for this thermal and load cycle. This means the presence of these reversible loss are recovered during this different cycle. After that, we have here reported a comparison of the polarization impedance spectroscopy before and after this durability test in steady state, the long thermal cycle. You can see that after both experiments, we have an increase of the onset of the cell voltage. This is due to the catalyst degradation. That's more evident in the impedance spectroscopy, as you can see. The blue curve is regarding the beginning of life. Red is after the steady state durability test, and green for the load and thermal cycle. The increase of the polarization resistance is due to the catalyst degradation, more evident for the test with the load and thermal cycle. It's more evident also during by the impedance spectroscopy at 1.8 volts, you can see a reduction of the series resistance before and after the durability test. This is probably due to the regarding the membrane. This means a cleaning or thinning of the membrane after the test. Okay, in order to understand what happened at our MEA after the durability test in steady state low thermal cycle, we have carried out the chemical-physical analysis after the test, and here reported a comparison of the MEA at the beginning of life and after these two different tests. We have an evidence of a good adhesion of the electrode of the membrane and no particular change in scanning electron microscopy in cross-section. We have an evidence of the thinning of the membrane after the two different tests, after both load and thermal and steady state, more evident for the steady state test. We have also analyzed the morphology before and after of the anode that was synthesized at CNR. We have observed the structure of the nanosize irregular shape and phased particle, and probably just less agglomerated after the both durability test. And what is happened in the XPS analysis? We have recorded a shift to lower binding energy. XPS analysis is surface analysis. So we have in evidence in the surface, the shift means the reduction of the iridium, but also for the ruthenium, we observed. And we have observed a formation of substoichiometric structure for the iridium and the ruthenium. We have also analyzed the morphology of the cathode side. That was 40% platinum carbon, and for the cathode side, we don't observe significant change in morphology before and after the both durability test. Probably just a slight grow the particle of the platinum for the cycle operation. Here I have reported a table that summarizes the results obtained by the chemical-physical analysis after this durability test. For the fresh and the MEA used, we have observed the membrane thinning from the fresh and the used MEA. By ADX analysis from scanning electron microscopy, this means in the bulk, we have observed a loss, especially for the MEA used in a loaded thermal cycle in the bulk, and also observed in the surface, as shown in the last slide. We have also evidence of the presence of the substoichiometric structure for the iridium and ruthenium after the durability test. And for the cathode, just an increase of the particle after the load and thermal cycle. Beside the presence of the substoichiometric oxide phase on the anode surface, the slight loss of the ruthenium species may represent another cause of the catalyst degradation performance. Especially, yes, associated to the cycle operation, and we have observed an increase the polarization resistance in the activation region from the polarization curve. In conclusion, we have analyzed the performance degradation for the in single cell for MEA in product change membrane device during the durability test in the steady state long thermal cycle. We have observed a reversible loss to the changing in the oxidation state of the surface of the electrocatalyst and also the supersaturation that can be removed, can be partially removed with the cycle, with change the current density. And we have also evidence of the reverse loss due to the degradation of the electrocatalyst, as we have observed by presence of the substoichiometric structure and the loss of the ruthenium, especially for the in the load and the cycle, load and thermal cycle. This experience was fundamental for us in order to produce a stable solid solution of the ruthenium oxide in order to avoid this degradation or loss of the ruthenium in the anode electrocatalyst. Thank you for your attention.
Question.
What is?
The ruthenium
is ruthenium is included in iridium in solid solution is 70% of the iridium and 30% of the ruthenium.
Degradation?
Yes.
Somewhere else?
Ruthenium
is dissolved.
Yeah, is dissolved.
The membrane, in the water.
No, we have observed after the durability test in ex situ analysis. We scrubbed the electrocatalyst from the, we prepared the CCM. So we have the catalyst included in the membrane. After the durability test and after the electrochemical characterization, we removed, scrubbed the electrocatalyst from the membrane and have the X-ray D, the scanning electron microscopy with the powder, the electrode removed by from the membrane. No, we don't see, we don't analyze this during the test. By CP, no, from water, no, not yet. Yeah.
I don't know where it
In
went.
principle, the ruthenium that is dissolving from the, in principle, the ruthenium that is dissolving from the anode catalyst is going through the ion exchange resin, and that is blocked as a catalyst.
You found it there?
No. It's not to be expected, but of course, these are, of course, very low catalyst loading with very few ppm or ppb, so very difficult to detect in the solution, but we expect that is anyhow blocked by the ion exchange resin coverage, because we didn't see any big change in conductivity of the water that is that the inlet of the sample. sorry, took those hydroxides of the green volatile. So in the chlor-alkali industry, we're also using this heavily. We used to trace anode degradation by making a big like isotope over the helium in the gas stream. So I've always suspected that with dealing with hydroxide, it's just so let's say if the price is going up, it's always quite nice.
Yeah.
This is why lithium cannot be used for oxygen generation in submarine or
But Elon, but Elon, if you create a solution, you can expect you expect that maintain with the in alloy with the iridium.
It does. It reduces the corrosion rate in a solid solution, but as you found yourself, reducing from loss of way less than if it's a physical mixture of which fuel would be oxide. The say chlor-alkali, that's how we just track it. So I suspect that's it.
In the chat.
I think you measure gas crossover. Because you go quite low current densities.
No, in this test, no.
And I don't know if you mentioned it yet, but chlorophylls and PTFs, are you using titanium or are you using coating?
Yes, we use titanium for the anode side and cigarette for the cathode side.
For this passivation or
no, the titanium is platinum, is commercial.
Thanks.
There are some questions in the chat. Maybe you want to scroll through them.
No, we have observed a decrease of the performance. In the first period, we have a decrease of performance that are interrupted when started the cycle. We have removed the reversible loss, the partially reversible loss. But in the first period, we have observed an increase of the potential value. We work in galvanostatic, and we have a decrease of the performance due to probably to the period of the cleaning of the membrane or thinning of membrane. This means reduce the resistance. Yes, it's possible to confirm because we this mass transportation is evident in the impedance spectroscopy. We have larger polarization resistance, and this is due to the mass transportation. And we have analyzed this problem in ex situ, and we have evidence of this problem for the anode side. The ionomer degradation, I think no, because I'm not sure probably very well the transmission electron microscopy, but we see the ionomer before and after the durability tests in both cases, in cycle and also steady state. We have a good presence of the ionomer, no loss of the ionomer after this durability test. Yeah. Yes, this is opinion. We don't analyze the membrane in scanning electron microscopy. We have evidence of the loss of the ruthenium in our electrocatalyst. I think we will check after another analysis because I have an experience that we have the presence in the membrane of the electrocatalyst. I used the no critical raw material, and we have evidence of the electrocatalytic membrane. But in this test, we don't analyze the membrane after the test.
It's
Okay, thanks.
thank you. Plenty of questions.
So we go to the next one. Felix?
Well, hello everybody. Thank you for the chance to present here today, especially of course to the organizers. And my name is Felix Lohmann-Richters. I'm from the Institute of Electrochemical Process Engineering in Jülich, Germany, the IK 14. And in the frame of the channel project, which has already been presented this morning, we have done some degradation tests and also electrode developments and everything as Louis presented. But I'd like to go a little bit more into degradation, monitoring, and for anode here, and then the harmonization of the protocols and the hardware in the project. And then also say a few things about the dynamic testing and AEL. So I'll go through it in this order. And to start with the performance and stability testing for this nickel-ion LEH, layer double hydroxide anode, we did a 1,000-hour test, which is shown here. We even did 1,600 hours, and it was still stable. But for this one, we have a very detailed analysis with the degradation tracking and XE2 analysis after several time intervals, as you can see indicated with the arrows down here. And we see, for example, here for the first 200 hours, we have an improvement, a reduction of cell voltage, and then there's a degradation afterwards with about 18 microvolts per hour at 1 amp per square centimeter. On the right-hand side, you see the images of the electrode and the membrane. They still look quite good after 1,000 hours. The color change is for the anode is normal, is to be expected for the layer double hydroxide. And then in the middle, you see the development of the ohmic resistance in black over time, which increases in the first about 200 to 300 hours, and then it's quite stable. That's very nice, because in AEM, we often discuss stability of membranes. So this looked really good. And then on the other hand, in blue, you see the charge transfer resistance, which decreases significantly in the first 200 hours and then starts to increase again. So there's an activation first, and then probably some kind of surface, electrochemical surface area loss. So let's take a closer look at that. When we look at the electrode XE2, we see that at the beginning it's more like an agglomerate, and after a while of testing, it becomes sponge-like. This is a kind of deep reconstruction that has also been observed in other kinds of electrodes, LDH, copper LDH electrodes, for example, cobalt LDH electrodes, for example. And when we look at the elemental composition of the electrode here in EDX, we see that there's an iron leaching, which is not completely surprising. This seems to be mostly taking place in the first 200 hours again. And we also see that this iron ends up in the electrolyte. So we have much more iron with the electrolyte afterwards. Summing this up, we basically can see this reconstruction of the catalyst layer. And if you keep in mind that the overall performance was surprisingly stable, with all these changes on the micro scale, I think that's actually quite surprising. Now, these measurements have been performed in Jülich in the channel project, but there were tests being done in Jülich and also at NTNU in Norway. And of course, we wanted to have a good comparison between these tests. And in the framework of the channel project, we defined a protocol to follow. And there was also this workshop with the NEWELY and NEWELY projects at the beginning to develop the harmonized protocol. And of course, we wanted to compare that. And we take a quick look at the protocols. Don't read all the details now, but the basic differences were that we have a different break-in procedure in the channel protocol. We basically did a 1 amp per square centimeter hold time before recording the first polarization curves for 4 hours. And then we had later on an open circuit potential step for 3 hours before recording a second polarization curve. And then the flow rates and the temperatures were a little bit different. And when we take a look now at what we measured in the channel project, let me guide you through this plot on the right-hand side. The blue curve, the blue triangles, are the results from the harmonized protocol measured at NTNU. And the black triangles are then the channel protocol. There's a slight offset here, and I would say that this is probably due to the 1 amp per square centimeter holding time. And then after the OCP period, we measured the open triangles, a significant improvement, actually. To me, that was a surprise. And then we measured the same, nominally the same electrodes in Jülich with the Jülich cell, and ended up with the green curves, which means lower performance and no influence of the OCP step. This was, of course, not desired, and we tried to figure out what that was due to. And one obvious thing was that the flow rates were not really the same due to the test stations, which have different ranges. We varied that, and we did not see much of an influence. So the flow rate was not the main point. With several more tests in the end, we came up with the point that it seems to be due to the single cell that was actually being used. We had 2 cell designs, one at NTNU and one in Jülich. And finally, we shipped the NTNU cell to Jülich and measured it there in our test station. And see now here the green curves from Jülich again, but with the NTNU cell, and they align quite well with the results from NTNU after the OCP period. Now, what we take from this is that we can get comparable results with the same single cell in different test stations, but the influence of this OCP step seems to be somehow related to the test station itself. And we cannot explain that yet, but it should definitely be looked at it closer. Now, what I have here on the right-hand side to illustrate a bit the differences between these cells, they are contact pressure distributions of these cells. In both the Jülich and the NTNU cell, the distribution is quite homogeneous. But the NTNU cell has parallel flow field, and in Jülich we have a serpentine flow field. And we would actually like to look a bit closer on the influence of the contact pressure. If we take a look at the usual cell, or let's say in this case the Jülich single cell, it consists, not surprisingly, of monopolar plates, gaskets around the electrodes and the separator. And the gaskets around the electrodes are basically what defines your compression of the electrode and the contact pressure as well. And if you want to change this, we need to disassemble the cell, reassemble it. That's very tedious and prone to error. So we came up with a cell design that allows to adjust the pressure on the active area. We have here a circular electrode on the right-hand side. And we also have a few more features in the cell, which we introduced to try to investigate the different local conditions in a larger cell or stack to bridge the gap between a single cell and a stack measurement. But that's ongoing work. Let's take a look at the cell from the side. You have these screws on the right-hand side to adjust the pressure on the active area. And the first results which we obtained with this are shown here. On the left-hand side, you have polarization curves for different contact pressures, and they actually overlap. They're all the same. However, if you look at the right-hand side, you see the crossover, the hydrogen and oxygen at 50 milliamps per square centimeter, and that increases a lot with the contact pressure. This is an effect that we've also seen in PEM electrolysis, and which is so far explained only in part to my knowledge. But this really makes clear that when we have a single cell measurement, depending on what we want to know, we need to pay a lot of attention to have really the same conditions for comparability. One thing that I forgot to mention when I showed you the single cell is we're using this cell now also in a liquid alkaline round robin testing together with several other international labs, and where the results are not there yet, but we're really looking forward into how it compares between the different labs. It will certainly be not the same everywhere, and then it will be interesting to figure out why. Now, that was about the hardware, and we have touched already before on the dynamics and the long-term testing of the electrolysis cells, and we have performed some classic alkaline electrolysis single-cell long-term tests here about 600 hours, and we applied different polarization or voltage profiles here, just stationary with a black curve. Those interruptions are due to recorded IV curves, and then triangle wave and square wave potentials. And you see that especially at the beginning, the current density at 2 volts behaves a bit differently. It decreases faster. You might say the conditioning is faster for the triangle wave and the square wave. Those vertical lines indicate when it reaches about 1% change per hour. What I'd like to illustrate here is that when we talk about conditioning and degradation, for me, it's an open question of at which time we define the transition, whether it really makes sense. These were pure nickel mesh electrodes, and it will depend a lot on the electrodes we're actually using. So for some commercial electrodes, we've seen much shorter break-in times. But if you now imagine these are 600 hours, and we would like to talk about 60,000 hours in terms of degradation rates and stability, this scale is, we would only see a very tiny fraction of what we're actually interested in. And in earlier presentations today, there were already different degradation rates given for different times of the long-term test. And I think this is something we need to look into a bit more to have really comparable degradation rates, because if everybody calculates it in a different way, it will be hard to figure out what's actually worth. Of course, we also tried to calculate degradation rates for this, and we came up with these results now here for the 1.8 volt hold stationary, and the triangle wave showed faster degradation. The square wave showed an even faster degradation, and this is maybe due to the ramp in between, so the speed of changing, which, if we think about the ASTs, might be a critical factor when we compress a profile. And then the last thing here, the wind profile, is highly dynamic. We have a wind profile here which has a 1 second resolution. So that kind of mimics when we have a wind turbine directly hooked up to our electrolyzer. And we also developed a way of extracting a polarization curve directly from this dynamic wind profile so that we do not have to interrupt the measurement to characterize it. And I think that's a very, very interesting thing that we will hopefully publish quite soon. And maybe this way of creating a wind profile is also something that's interesting for the common testing procedures and profiles. For this, I'd like to sum up. We had this degradation first with the AEM, EL, the harmonization of the protocols is needed, but we saw that our cells also have a huge impact. Test station as well. And the contact pressure is especially important for the crossover, and we should definitely look into dynamics a bit more and get to the same definitions. I'd like to acknowledge channel funding, of course, and then also the next H2 project funding from Germany. And thank you all for your attention.
Thank you for this. I was wondering, you mentioned you have a wind turbine connected to an electrolyzer. Can you elaborate on this apparatus?
No, we don't have a wind turbine, but we have high resolution wind data, and we have a model to calculate the power output of a wind turbine, which is in this wind, depending on the mechanical properties of the wind turbine and all that stuff. And now we feed this profile that we create based on the wind data into our electrolyzer test station.
What's the capacity of the electrolyzer?
Oh, this was just scaled to a single cell then, so just a few square centimeters. But we've also tried to do that, if I remember correctly, my colleagues from the PEM department, they tested that with a 100 or 50 kilowatt PEM stack, and apparently the test station took it quite well.
Thank you so much for your presentation regarding the dynamics analysis of dynamics. Did you change the potential of the current? I didn't follow.
In this case, we changed the potential. Yeah. We were wondering what would be better, and we decided to take the potential to avoid any excessively high potentials, which might trigger different degradation mechanisms.
Usually, degradation, durability tests are usually carried out in a galvanostatic mode. It measures the. So, if you fix if you change the potential, how it is possible to determine the degradation rate in terms of microvolt per hour? Because here is micron.
You're right. The first one, with the AEM, we did that with constant potential, constant current, and this one was with constant potential. But with this dynamic wind profile, we can actually extract it both ways, either, which is nice for the comparability.
And then you try doing some, analysis using varying the potential, the current instead of potential.
For the alkaline, not yet. No. We'd like to do that, but we haven't got that.
Can I ask another question, possibly? Regarding the analysis of the degradation of the nickel iron or later the double hydroxide that we presented in the first slides, I was wondering what kind of cathode have you used, and if you have used a reference element, how were you able to deconvolute the degradation of the anode from that of the cathode?
Yeah, that's a good question. We have not had a reference electrode in the cell, and as far as I know, I'm not an expert on these reference electrodes for cell measurements, but as far as I know, the placement of the electrode is very delicate, and we really need to pay attention to what exactly we can interpret with that or not. But the cathode was platinum on carbon cathode as a benchmark material. which we have used in the channel project also as a benchmark throughout the whole project. And so there is not much of a deconvolution which we could do with the impedance spectra or the other electrochemical techniques. Would be very interesting. I'd love to do that, but I'm not sure how to get it really precise.
Thank you. You showed some data related to the hydrogen and oxygen content depending on the damping pressure. Do you have data on the thickness of the membrane as a function of the damping pressure?
We have
Compressibility tests.
We have, so this, to be clear, this has been done with the alkaline electrolysis cell, not with the AEM. But of course, the question is the same for both, right? And we have performed tomography measurements with different contact pressures with nickel foam electrodes. And there we basically saw that it's the electrodes were deformed and not so much the silicon separator. But we've also seen in different tests that if we put too much pressure, we can actually destroy the separator. So in this case, I'm pretty sure that we did not change the separator a lot. It's more the contact, the electrodes which deform, but that depends very much on the actual separator that we're using. It might be different for different membranes.
Did you see the HDL breaking after a while?
In which system? Here in in this one, here we have nickel foam as the basic PTL, and that does not break. No, that's it. No carbon.
Just for me, one remark in the report with different rates and different exposure times. So in the report we took the raster approach, which is by multiplying the degradation rate with a factor of 1,000 hours divided by the extra exposure time.
So the question, if so the first question about the compression ratio for the foam and the zircon as a parameter, yes, it's something that we try to keep constant for comparable measurements, which we'd like to investigate more with this second cell that I have shown, where we can adjust the compression. So that's subject to investigations. And the second question here. So the electrode degradation being more critical than the membrane for the AEMEL. I think the membranes are getting more and more better. They're considering what we had a few years ago, it's a really impressive development. I don't think that we need to stop that, but I think that now that the membranes are good enough, we see that our electrodes are maybe not yet good enough. And especially the electrode design and the ionomers in there. And earlier today, it was mentioned also the ionomer catalyst interaction. That's still, we still need to do a lot of about that. But I wouldn't dare saying that we should focus much more on the electrode. We need to put both of them on. Another one? No, that's not us. Yeah.
Okay, thank you.
Thank you.
Yeah.
Okay, thank you. First of all, for inviting me to present this work on accelerated stress tests on proton exchange membranes. As the title suggests, we very much try to take a component-specific approach towards accelerated stress testing. This work is very much work in progress, so it's an iterative cycle, literature review, experimental validation, and so forth. So, and what we want to do is to isolate as much as possible the degradation phenomena for the specific components. So I will give a brief outline of the general framework of thought behind the stress test that we've developed. And then in view of time, I will only focus on the anode catalyst degradation, which in itself is already quite a complex phenomenon. But first of all, I will give a brief introduction to TNO, the Netherlands Organization for Applied Scientific Research. So we are active in many electrolyzer technologies. So we're based in Petten, just north of Amsterdam. And we have a site in Groningen. So on the left panel, you can see that we can do tests at smaller active areas. So 1 square centimeter, where we have test stations that can run multiple tests in parallel. Typically, we also have 10 square centimeter. And in Groningen, we have the Hydro Hub, which consists of 2 stacks of 250 kilowatts, one focusing on alkaline technology and the other one on PEM electrolysis. So yeah, in that way, we try to, at the small scale, try to understand the complex degradation mechanisms that underpin the degradation of the components. And also, beyond that, transcending to that, to have an understanding of what happens at a larger scale on an industrial sized stack. We already, I think, touched this topic earlier today. You have different test philosophies where you have accelerated life testing protocol that generally have mild stressors. They try to mimic the operational envelope that you have, and they are less targeted than compared to the ASTs that you see on the left-hand side. And of course, they mimic maybe real-life conditions very well, but in terms of interpretation, they are somewhat difficult to kind of disentangle the different degradation phenomena that can be at play concurrently. So instead, we focus more on accelerated stress tests, where we apply a harsh stressor that's really targeted to a specific degradation mechanism of a component. And indeed, we have, as also mentioned earlier, there's this compression factor. We try to accelerate and drive that degradation phenomenon to the maximum. There's always a risk when you have this harsh stressor that you kind of exaggerate and that you will end up with a condition that is not fully representative of the typical use case that you have in mind. So the ASTs are more intended to do kind of rapid screening, in our belief, to see what works, what doesn't work, and only if you have and to understand the mechanisms that underpin the degradation, and then you can move on to ALTs. So that I will focus on the AST mainly. Okay, we all know they need the irreversible losses, and we identify different component groups. The hydrogen evolution reaction is that quick that we kind of, for the moment, put that aside and focus more on the somewhat sluggish or slower anode kinetics. Of course, you have the dissolution, if you the loss of catalytic mass, and of course, macroscopically that manifests itself as an increase of polarization resistance. Going also to lower loadings, the catalyst layer resistance will play a role, and the homogeneity of the catalyst layer will play an increasingly more important role. And of course, you have the passivation phenomena, and going at elevated temperatures, you have radical formation due to oxygen crossover, which predominantly will attack the membrane on the cathode side. Let's see. Yeah, so we have identified certain stressors, and we have assigned them to components. It's clear that all those stressors that you see here, the elevated temperature, on-off behavior, potential cycling, high voltage, and low humidity will degrade the anode catalyst layer. For the PTL and the bipolar plates, well, they used to be titanium, and now there's more and more efforts to move, especially for the bipolar plates, to stainless steel, due to the fact that even titanium becomes a critical raw material nowadays. Indeed, the high temperature plays a role. So you have diffusion of oxygen through your lattice. Usually that could be field assisted. But also the local pH and the local corrosion potential play a role, and especially the PTL will take the biggest brunt there. And I will not go into the details of the membrane test, but of course that also radical formation is temperature activated. At moderate current densities, you will generate quite a few hydroxyl radicals there, and what we're not testing at our lab at least is a low humidity. So let's focus now on the anode catalyst. For PEM, of course, they are PGM based. Well, with only 7 to 8 metric tons per year production, it's important to lower the iridium consumption and to enhance the catalyst utilization. And with the state of art, like the relatively high loadings, the anode catalyst degradation is somewhat masked by the excess of catalyst. As we are going down in loading, catalyst utilization will become increasingly more important. So this is just an overview of all the gamut of all the effects that are out there, also in literature, based on literature studies. So we have change of oxidation state. So on the left panel, you see X-ray absorption spectroscopy, where there's a shift with oxidation state with the oxidation state of the catalyst. Of course, going to higher potentials could drive iridium dissolution, and then even if you use an electrolyzer in conjunction with renewable energy, load cycling will be an important part. The operational envelope plays a really big important role here as well. Are you going to switch off your electrolyzer? Are you going to run a protective current? And it's like, even though we're here still on the single cell level, all these things transcend towards stack level. Likewise, if you cycle your potential, it will dissolve your anode catalyst, it will redeposit. You get a kind of Oswald ripening, or kind of growth of particles, changing the pore size, giving an unfavorable area to volume ratio, which all induces kinetic losses. And of course, you can have phase transformations that could affect the intrinsic iridium catalytic activity and the stability, and also the resistance of the catalyst layer itself. So then, if you in a literature review, we found like two main approaches towards accelerated stress testing. Indeed, the NREL protocol that that focuses more on load cycling of potentials. They used several stressor waveforms, constant load, triangular waveforms, sawtooth patterns, and block pulse wave patterns. And it's obvious that for load cycling, the block pulse is the most degrading pulse. And then, of course, you can play with the cycle time. In general, the faster you cycle, the faster you degrade for the equivalent amount of time. That is one aspect. And now we also have to look at shutdown behavior, where the very moment that you kind of shut down your system, you get a kind of permeation flux or crossover of hydrogen towards your anode catalyst, which reduces it, which can, if you start off with the rutile phase, for example, change the ohmic resistance of your catalyst layer. So both effects should be taken into account also in an operational strategy. And then, of course, for your ALT, it matters what kind of application you have in mind, what you're going to use. But eventually, you have to shut down your stack, of course. Okay, so this is an overview built based on those results. We, at this moment, focus mostly on load cycling. So you can see in the middle panel is that we apply this block pulse stressor, and that is interspersed with in situ characterization, so polarization curves, impedance spectroscopy. But indeed, before that, we take a beginning of life fingerprint of the device, and then after in 166-hour intervals, after 5,000 of those cycles of this block pulse waveform, we collect polarization data and impedance spectroscopy. We use already a lower loading of the anode catalyst layer, just to kind of exacerbate the degradation phenomena that we want to see. But actually, in the future, we want to go even to lower loadings, to see even a more pronounced effect. Our cathode layer is not so much under consideration. It will probably degrade, but it's just the standard half mgs per square centimeter. And of course, to rule out any passivation phenomena at the higher potential level that we're using, we have plated all the titanium parts with platinum. And we deliberately choose a lower temperature. So instead of 80 degrees, we moved a bit down in temperature, because we want to kind of specifically stress the anode catalyst layer. So all the formation of hydroxyl radicals or potential membrane degradation, they are kind of suppressed. We use molecule water, so even to rule out as many other effects that you could have in this kind of block pulse waveform. And having a lower temperature, that also means that our potential is stepped up a bit of the 2 volts that you would expect. So we use 2.275 volts to compensate for that extra ohmic overpotential that you would have due to the lower proton conductivity at 60 degrees. Conditioning is not unimportant, and it is, I think, probably going to be a challenge also to standardize that for each and every component set. So yeah, there's different approaches there, and we just use the preheating at 40 degrees, and then we heat to 80 degrees, and then only then we apply 2 volts for 24 hours. The polarization data and the electrical impedance spectrum is only going to give you only that much data. So of course, for each sample, we take also witness sample in its pristine state for ex situ characterization, and also for the aged sample, we're going to apply a different characterization techniques. This standard electron microscopy, transmission electron microscopy to look at the particle coarsening, and the oxidation states with XPS and xanes. And last but not least, the conductivity for both states. The next steps will be also to consider the shutdown behavior, where we completely lower the voltage. So if we look at the in situ data that we have collected so far, when we can see indeed that there is indeed a increase of the polarization resistance. So what we collected is indeed all these Nyquist domes that start to project outwards towards higher polarization resistances. We used a fairly simple equivalent circuit just to kind of use Occam's razor to not overcomplicate things and to interpret things that are phenomena that are not strictly there necessarily. So we use a series resistance, constant phase element, and polarization resistance, and then indeed you see that you get indeed an increased polarization resistance. But on top of that, there's this gradual drift of the ohmic loss. So actually, the membrane may either thin ever so slightly, or there's some creep, which gives the kind of smaller distance for the protons to transit. There could be something going on in the catalyst layer, or maybe we have to revisit our conditioning state, and that's indeed a big discussion. Where is your break-in time in your actual test? And likewise, if you look at different the current density at 2 volts and 1.6 volts respectively. So 1.6 volt would be more like a representative of the kinetic behavior, and 2 volts is more the ohmic component. Then indeed you see a kind of similar corresponding trend. Then indeed, to conclude, we have a protocol that for at least for load cycling that effectively degrades our catalyst. I think as we speak, we were continuing with the ex situ characterizations to have an idea about the particle morphology, the oxidation state, and to kind of corroborate what we are actually seeing in the impedance data and the polarization curves. And the next steps would definitely be also to look at the cycling frequency. So the Gasteiger of the University of Munich group, they use a 10-minute cycling time. So we're going to compare 1 minute against 10 minutes, also against steady state. And I think indeed this is also pushing the boundary for thrifting of iridium. We really have to go even lower with our iridium loading. Yeah, that's it. Thank you.
Question.
In two volts, I see an increase of carbon density with time. It is a bit, or is my understanding is not correct?
Yeah, it's if you actually look at the polarization data, you see indeed that at higher current densities, that slope is kind of leveling. That there's a change of slope. So I think there's indeed something going on in the ohmic part of your chain. What exactly we have to find out. But if you go at like moderate current densities, then you see kind of trend upwards of your kinetic overpotential. Yeah.
It's 1,000 hours.
This is yeah. So it's in blocks of 166 hours, and then 6 times adding up 2,000 hours. Yeah. at this moment, we are still collecting the data. So indeed, of course, we need to look at SEM TEM data, SEM data to corroborate actually what we're seeing. So this is still a bit too early stage to draw the conclusions. And yeah, also as to why this ohmic drift is there, which it could be conditioning, but it may as well be that there's something going on in the catalyst layer or the PTL interface. Who knows? That is follow-up work. Yeah.
Regarding the potential cycling, I'm still a little bit, let's say, not in favor of potential cycling corresponding versus the current cycling. And I can also say why, my opinion, would be better the current cycling, because as an example, in this case, the upper potential limit is 2.275 volts.
Yeah.
And some electrolyzers manufactured have as the cut-off voltage 2.2, that means end of life. The reason is that because the efficiency, the voltage efficiency is so low that it is not of much interest to explore such extreme conditions. A practical electrolyzer will be shut down upon reaching such a high voltage because of, there is no interest. The cost of renewable electricity is so high. If the electrolyzer operates at very low efficiency, there is no reason to continue. And exploring such extreme limit, could be an indication. It would be good for understanding, but probably still not linked to the real life operation.
Well, I would say maybe just drop that potential across your membrane, and then maybe the catalyst that is maybe you would like to have in the actual direction along the stack. You want to probe what actually is going on. That will be even better. So the only reason we did that was that, like, going to lower temperatures just to. But I agree at 80 degrees, this will be in not favorable. So we just made that extra. We added that step based on our expectations, how much the proton conductivity of our membrane would drop. But
The observation is that I will not say that it's not important because, of course, any experiment that important in terms because it provides some attention, because we need much more people. But I'm saying that probably it is such an extreme condition that probably not much useful to, let's say, understand the real life of the system.
Well, yeah, it's like going to lower temperatures. Yeah, that's it. And for indeed the choice where we use current density or potential, that's also it also depends. We chose potential because we think it's a more generic approach that might last longer. Because indeed, if you go to thinner membranes, you end up at a different potential. So for the anode catalyst, we based our expectation based on potential. Yeah, and eventually it's just one way or the other. You measure the current density change at bit potential or the other way around. So that is and that you can also see in the work of the University of Münster that they use current density. Okay, hopefully that's Yeah, that's correct. Yeah. Oh, yeah. Yes, we're using a platinum coated PTLs and bipolar plates. Yeah.
Right. And you are observing a decrease on the ohmic resistance over time.
Yes. Yeah.
So then you might want to check your previous work in the lab to explain that why is happening that. Basically, you are losing yoga from the catalyst layer.
Potentially, yes. One of the things. Yeah.
So that and also in the membrane. Anything, let's say, you don't see it. And then your catalyst layer becomes more conductive, and that's why now the interface is more conductive. And we observe as well, what you observe that Well, you go, you can go next one.
The next slide, the one following this one, right? Yeah, okay.
Yeah. You see, the current is increased at 2 volts. It's increasing over time. So apparently your electrolyzer is becoming better, right?
The ohmic, yeah, losses are becoming less. Yeah, yeah.
But not at low voltages.
Yeah, yeah.
That is becoming worse. So
Yeah.
if you're observing the polarization curves, like they cross.
Yeah,
over time.
exactly.
So they are, I would say the papers.
Okay. Oh yeah, we're most interested. Yeah, yeah. Yeah, I need it. It's hard to tell without the extra complementary data set what actually, but indeed, it isn't quite useful.
Current density, the Calvin layer is performing worse because of the kinetics.
Yeah. Yeah.
But at higher current densities, then the ohmic resistance is lower, and apparently your electrolyzer is performing better. But it's degraded at some point.
Yeah, yeah.
Cannot be losing all the time.
No, exactly. Yeah, yeah.
Probably on a shorter time window.
1,000 hours.
Yeah, it started now as it was something unusual, but of course it depends on the ionomer content in the catalyst layer, and of course an optimization study of the ionomer content in the catalyst layer can probably reduce this phenomenon to such, let's say, an initial period. But I was curious to learn what was your interpretation of the phenomenon, and in terms of structural changes as a clearly.
Just observe it, and you have very good PPLs and that for place, reflecting focus. Because if you don't have it, then the passivation and also
there is another effect that is dominant. Yeah,
then it's going up.
Yeah, that's clear. That's very clear now. That's great.
Oh, yeah. So ohmic, okay, this is just a comment or, oh yeah, ohmic resistance is usually increased due to component degradation. Okay, did you observe it? Well, we didn't observe an increase of ohmic resistance indeed, because we used everything, plated everything in platinum. I think that, okay. And did you separate the ohmic resistance of the membrane from the ohmic resistance of the mechanical components? If yes, how did you do it? Yeah, I think there was an earlier comment on that. You might be able to tease out this information using the activation energy of your proton conduction, but it's probably at that point it becomes a kind of projection or a best guess. It's difficult to disentangle the ohmic components. Then you would actually have to use a potential to sense your potential maybe in your cell. Please also, okay, there is the. Do you think when you stop the aging for IV and ice, it affects the aging? If so, how do you define them a moment when you stop the aging for IV measurements? Well, what we do is we keep a small current. We never